We recently went to Blayland and we saw many physics concepts in the rides. Today we're here to show you how these concepts work, examples of them, and where you can find them in Playland. Inertia. Let's look at inertia. In Newton's first law, it states that an object in motion will stay in motion, and an object at rest will stay in rest unless acted upon by an external force. This is also known as the law of inertia. Inertia plays a big role on many of the rides at Blayland, but one of the rides its impact is most evident on is the pirate ship. How it works is that a motor pushes the ship in an upwards direction to get started, and then the motor is no longer required as the ride could just use its inertia to keep moving after it's reached its initial height. When the ship reaches its peak at either side, gravity pulls it down and inertia pulls the object back into the air, however never passing the previous peak unless it acted upon by an external force. To stop this ride, an external force must be applied in the form of brakes, or this ride would continue going for a long time without stopping. Apparent weight. Let's take a look at apparent weight. Apparent weight is defined as an object's weight due to gravity and other external forces on the mass. Simply defined, it's basically the normal force, or the force that the ground or any other surface pushes back with. We can see evidence of both increased apparent weight and decreased apparent weight on many of the rides which go up and down, such as the elevator or any other elevator style rides. I would like to show you multiple rides as an example for increase and decrease in apparent weight, but we can see it all on the elevator. A simple rule of thumb to keep with this is that when an elevator increases its speed while going up or decreases its speed while going down, one feels its feet pressed by the floor more than usual, meaning increased apparent weight. When the elevator decreases its speed while going up or increases its speed while going down, one feels their feet pressed by the floor less than usual, meaning decreased apparent weight. Let's solve this problem. Pause it yourself to try. Here are our givens. Here we find acceleration. And now we calculate apparent weight by plugging it in this formula. Good job if you solved it. Conservation of energy.
This is the coaster.
Hello, darkness, my old friend.
Next we have conservation of energy. We're going to be looking at kinetic energy to potential energy and potential energy to kinetic. Potential energy is the energy that an object possesses because of its position relative to another object, or PE equals mgh, and kinetic energy is the energy that an object possesses due to its motion, KE equals 1/2 mv squared. We can see evidence of both types of energy multiple times in the system of a roller coaster. At the top of the roller coaster, before it goes down the hill, it has great potential energy relative to the ground due to its height, and limited kinetic energy because it has little to no velocity. Once the roller coaster begins to head down, the height decreases and the velocity increases. Now if we look at the formulas that I told you earlier, height is decreasing, so potential energy is decreasing, and velocity is increasing, so kinetic energy is increasing. Potential to kinetic. Let's do kinetic to potential. So let's suppose the roller coaster is going at a decent speed, enough to get up a hill, meaning it has an amount of kinetic energy, and the roller coaster isn't really that high relative to the ground, meaning low potential energy. As the roller coaster begins to go up that hill and reaches the peak, it begins to slow down so that it can kind of scare the riders before it drops. As the velocity slows down, kinetic energy goes down, and as the height increases, potential energy increases. This demonstrates kinetic to potential energy. Conservation of momentum. Conservation of momentum means that momentum in the system is conserved. This is evident in the bumper cars which collide all the time. Neglecting any external forces, suppose you had one car traveling to the right with a momentum of 10 km/s and one car traveling left with a momentum of 5 km/s, then move to the right together at 5 km/s after the collision, meaning momentum is conserved.